So now let's look at anodized aluminum oxide. So in this aluminum anodization, so we put the aluminum film as the anode. The cathode is the platinum film. So we know that for the electrochemical process, the anode material will be oxidized, and there will be oxidation in the anode and reduction in the cathode. As a result, aluminum film will be oxidized. So there is the oxidation process. So we have the oxidation process. So on the other hand, so the electrolyte here contains acid like oxalic acid, phosphoric acid, and sulfuric acid. So those acids will act with aluminum or aluminum oxide. So there is also this dissolving process. So the net result is that you form this very deep pores in the aluminum. So in the end, the aluminum is all converted into the aluminum oxide. You have the pores inside the aluminum oxide. So there's the overall chemical reaction. So aluminum with water form aluminum oxide and hydrogen. So here's the structure. So this structure here is shown again here. So we have this pore, in the aluminum oxide, At the bottom we have this barrier. We have this barrier layer here. What do you see here? This is the bottom surface of the AO. AO means anodized aluminum oxide. Anodized. This is the anodized aluminum oxide. Sorry, it's here. AO. So anodized aluminum oxide. So the bottom part this is aluminum oxide. So this is the top view, and this is the filter. This is filter from the company called Wasserman. So this kind of nanopore can be used as a filter. So what is the advantage for this filter compared to other types of filters? So first, so this material, so aluminum oxide. So this one is inorganic. So inorganic means it will not be attacked by most of the solvent. So we want to filter some solvent with some solvent, and this will be safe. But we know that some solvent may attack aluminum oxide, but most solvent will not attack this aluminum oxide. So this is advantage for it. The other popular material for the filter is the polycarbonate. So polycarbonate is also a popular filter material. So in that case, this polycarbonate is made by the ion track edge by this method. So what do you do? So you have this polycarbonate sheet. You have the polycarbonate sheet, and you have these ions. So those ions are very high energy. This is like a micro electron volt. So micro electron volt ions coming from the nuclear reaction. So those ions come from the nuclear reaction. Because energy is very high, it will pass through. It will pass very perpendicular, to the surface. It will pass through. So along the track, this is the ion track. That's why I said ion track edge. So this ion, when it pass through, this area here will be damaged. So those tracks will be damaged, and then you can use some developer to remove the damaged part of this polycarbonate. This way you get this hole, you get this pore. This way it's made of a polycarbonate. It's also possible to make of other materials, but this is the polymer filter, and this one is the inorganic material filter. So as we see that there are two types of the process. So one is the oxidation and dissolving. So here we have this oxidation and dissolving. So there are two parts. They will compete. Then it's from this process. This is the barrier. So this barrier. But this barrier here has to be thin enough. Has to be thin, so that the oxygen ions can transport through the barrier. Aluminum ion can also transport through the barrier. And during this process, aluminum gets oxidized. Then it will push upward. So the wall is pushed upward by this continuous anodization process. But this is one mechanism for the aluminum oxidation process. But this is why not so not so clear. For example, we work with silicon. Can we do something similar? For silicon? This will not work. For silicon, you can also do the anodization. What you get will be, you will get a porous silicon. You get porous, you use the HF hydrofluoric acid as the electrolyte, you get a porous silicon. But here the pore is like a deep hole, But here for the critical silicon, so the pore for the critical silicon, the pore is like a 3D random pore. It's not like a vertical pore. You have the pore everywhere, like a sphere. Each of the pore like a sphere shape. You got this a porous silicon like a sponge. So this porous silicon is like a sponge. But here you get this very nice, deep, very, very deep holes. So this will not happen for the silicon, for the case of silicon, unless it will shine the light from other side. So this way you can form this vertical pores. So where will the form? Where the pore will be formed? So when you put this, when you start the experiment, so first, at the very beginning, it will form the barrier oxide because you put this as the anode. We have anode, anode gets oxidized. So you have this oxide formed right away. This aluminum, the surface will be oxidized right away. This is the field distribution, electrical field distribution. You can see because of the roughness of the surface, the film cannot be perfectly smooth. You get this roughness. You can see the field, electrical field line is always perpendicular to the surface. This area here has high field. This, for example, the area like this has very high field. So we have higher field. There will be more etching. So as a result, the area here, will be etched more and more. The area here will be etched, and this area also etched more and more. So those area here, the field is not very high. There will be no etching. So as a result, some pores will stop growing. So some pores will stop growing because of the competition among the pores. So there is competition among the pores. So when some pores grow deeper, it will grow faster and faster. As a result, they will keep growing. The other pore, it will stop growing. Then you eventually get a stable pore growth. So now the question is, so why electrical field is perpendicular to the surface? Why the electrical field is perpendicular to the surface? So we know that for the case of the metal, for instance, we have this metal, like a aluminum metal. If we have the metal, the E field, electrical field, is always perpendicular to the local surface, because here we have lots of electrons. If the field is not perpendicular, electrons will move around, such that in the end, electrical field will always be perpendicular to the local surface. But here, this is aluminum oxide. We have this oxide. This is why not metal. If this is not metal, how come the field is also perpendicular to the surface? Yeah. So this is because, so even though the aluminum oxide, this one is not a metal, but here we have lots of ions. So the electrolyte is actually like a metal. It conducts current. So the electrolyte itself is conducting. So the field has to be perpendicular to the electrolyte, and this way is also perpendicular to the aluminum oxide surface. Here the dimension of the anodized aluminum, the nanopores. So the parameter to control is the voltage, the type of electrolyte, temperature, and time. So the cell size, the D is typically 2.5 times the applied voltage. So V is in the unit of volt. The diameter of the pore is on the order of the voltage, but the pore can be enlarged by acid. You can do some isotropic etching to make the pore bigger. So here are three typical examples of the electrolyte. The first choice is the sulfuric acid. For the critical sulfuric acid, we use small voltage. So we have small voltage. By this formula here, smaller voltage give you smaller inner pore distance. So this way you see, so 25 times 2.5 is roughly 66 nanometer. For the second choice is the oxalic acid. This is why you work with 40 volt, 0.3 mole per liter. You get then 40 times 2.5 give you 1.5 nanometer. The third one is the phosphoric acid, 195 volt, 195 times 2.5 volt, 2.5 give you about 500 nanometer. Now this is the typical three conditions for the anodization. So depending on the diameter you want, you can choose different acids. Other conditions will also work. Other voltage, other conditions will also work. But those conditions give you the good ordering. So this is the inner pore distance. the pore diameter in the pore thickness, those numbers here looks like something. For example, this number here, they are not so right. But you don't worry about that. The main thing is the inner pore distance dependent on the voltage. So we want to make use of the AO. To make use of AO, as we said, one popular application is to make the filters. For the filter application, for this filter application, we need to remove. So we need to remove aluminum on the bottom and also remove the barrier layer. Then we have this filter. This is can be used as filter. Now to remove aluminum, we can use mercury chloride to activate the aluminum. To remove the barrier layer here, we can use the phosphoric acid. So after the removal, you get this structure, as you can see here. Now this kind of membrane, you can buy it. You can buy from company like Westman. You can buy like normally 60 micrometer thick. The height is 60 micrometer. The power size is down to 20 nanometer. So you can buy this one. You can use it as a filter. The cost is not very high. It's a few dollars per 1 inch. A few dollars per 1 inch size of the filter. But this 20 nanometer is only one side. And what do you have here? What do you think? In this case, you see the top side of the power is the same as the bottom side of the power. But the filter you bought, I know a professor from the mechanical engineering, so he bought the filter and he found out that he wants to use 20 nanometer power, but it's only one side. The other side is bigger power. So how to make the power that has different size? So what you do this way. You do this way, then you branch it. So this part is bigger, bigger distance. So this part is if you look at here, higher voltage. So higher voltage give you bigger spacing and also bigger pulse. So first you start with the higher voltage, then you use, when you go to come this one, you use the lower voltage. So we have the lower voltage, the power density will be higher. You get smaller power and also denser power. This way, so this side can be 20 nanometer. But this side here, the power side here may be 100 nanometer. So here are the chemicals. We talk about mercury chloride and to activate the barrier. So here are the chemicals involved in the nanofabrication using AO. So first, we want to activate the aluminum. We want to activate the aluminum without attacking this aluminum oxide. And this is done by this mercury chloride. Sometimes we want to remove AO. We want to remove this part without attacking the bottom aluminum. This is done by this one, the mixture of phosphoric acid and H2CrO4. You can remove aluminum oxide without attacking aluminum. You also need to remove the barrier layer. The barrier layer at the bottom, you remove the barrier layer to make it flow through pores. This can be done by using diluted phosphoric acid. So as we have seen for the block copolymer cell assembly, so sometimes we want guided growth, aligned growth, and we want some long-range ordering. So we want very good periodicity. We want to improve the periodicity. How to do this? So one way to do this is to do the called a two-step anodization process. So I think this is a very smart idea. You do not need to do any lithography. You just do the wet chemical process. You get pretty good periodic nanopower. So what do you do? So first, you anneal aluminum. So this is the aluminum sheet at 500 degrees for 3 hours to increase the grain size. Your grain size. We have bigger grain. You have smaller grain boundary. Then you do electropolishing in the solution of this HCrO4 and acetic acid. Not acid. This is the ethanol for the 4 minutes at this voltage. So you polish, make it smooth. Then you do the first anodization. So the location of the power is determined here. So the location of the power you can see is random. So you get this random location because of the roughness. The roughness of the surface is random. So you get this random location on the top surface. But when the power grows deeper and deeper, you see at the bottom of the power, they are more periodic. You see the distance between the pores, they are more periodic. Then you remove this top aluminum oxide by using this chemical. So this one, you can remove aluminum oxide. You leave behind this aluminum. You have some aluminum like this. Then you do a second anodization. When you do the second anodization, this part is like the guiding pattern. So the part will grow at those position. You get very, very nice long-range periodic part. So as I said, this one is very good because you do not need to do any lithography. It's cheap. So obviously you can also do the lithography. In this case, you can easily using focused ion beam to drill some holes in the aluminum. So when you drill the hole in the aluminum, then you do the anodization. Obviously, the anodization will follow the hole pattern. So again, so the hole drilled, the hole etched by FIB, the period of the hole etched by FIB should match the natural period of the anodization process. So you can see here. So when they match, you get very perfect array, very perfect array. So this one we have this mismatch. For example, this one is minus 80% mismatch. That means the whole period by the FIB is different from the natural period by 80%. You see there's some defect. There's some defect. This is the 6% difference. This one is unguided. When they're unguided, you see there short range ordering but no long range ordering. Another way to make some dimple, to make some holes, we need to make some holes to get the growth. Another way to do this is to do it by the imprint. We can do the imprint, non-imprint, to make the holes in the aluminum. So aluminum is relatively soft. Aluminum is softer than nickel. So we can use nickel mode to make some holes into the aluminum. Then we do the non-imprinted process. In this case, we need a pretty high pressure, 1,000 atmosphere. So normally when we do non-imprint, we only need 20 atmosphere. But here it's 1,000 atmosphere. Because aluminum is still like a metal, it's hard to press. So there are two ways. Here we show the two ways to make this nickel mode. The first one, you do the photoresist pattern. Then you coat the metal on the top by some angle evaporation. You tilt the wafer. Then you do the evaporation. You will coat the metal on the top, not the metal on the bottom. Then you do the electroplating, nickel electroplating. Then you remove the other layer. You get this nickel mode. You can also do the KOH etching. KOH. So we know that the KOH etches the silicon anisotropically. They have this etching pattern. This is like a V-shaped pattern, pyramid, inverse pyramid. This plane here, this is the 111 plane. Then you coat some gold at connecting layer. You do the electroplating. You remove the silicon. You get this nickel mode again. Then you can press into the aluminum and you do the anodization. You get very, very nicely ordered pattern. As you can see here, this is the hexagonal array. You can even make a square array. You can even make a square arrangement. But this is very different. So normally we know we get this hexagonal array, but by this pre-patterned aluminum, with the square array of the holes, you get this kind of a square array. So this is very exceptional, I think. If we keep going, you can have very, very high aspect ratio, very, very high aspect ratio periodic patterns. So no other etching technique. No other etching techniques can give you this high aspect ratio holes. So previously we have seen that we can get very high aspect ratio pillars. So this is the substrate we grow a pillar. So how to grow a pillar like this? How to grow a very, very high aspect ratio pillar like this? So we have seen that this can be done by using IBID, ion beam induced deposition. It's also called FIB CVD, right? We can use ion beam induced deposition to give you extremely high aspect ratio pillars. By this aluminum anodization, we get extremely high aspect ratio holes. So now let's look at what's the use of AO for the nano fabrication. So the obvious application is to make the nanowires. You can see you coat some gold electrode as the connecting layer. Then you do the electroplating, and you cover the backside with some epoxy. Cover the backside with epoxy. Then you do electroplating. You get this very, very long high aspect ratio nanowires. So this is one of the main applications of the anodized aluminum. You get nanowire growth. So here's the second type of application. So here you have this AEO, you put it on the gallium nitride. So what is the use of gallium nitride? So we know that the light, the bulb, the LED bulb is made of gallium nitride. So this is what gallium nitride. So this gallium nitride is give you the blue color. So this one give you the blue color. But we know the LED light is a white color. How do you get white color? So what do? So you have this blue color light come in. I put some phosphor. So you put some yellow phosphor here. Yellow phosphor. So at the end, so there will be some. This is the yellow color phosphorus material. So you have blue color. Some blue color will also come through. So you have a mixture of this yellow color and blue color. If you adjust the well the yellow and blue color, you get the white light. You get the white light. So this main application for gallium nitride is for the lighting. It's also used for the blue, blue. It's also used for the Blu-ray. But nowadays nobody uses Blu-ray or DVD. So here you can put the AO on top of the gallium nitride. Then you can do the etching process. This way you add some nanopore in the gallium nitride. And another way you do some e-beam evaporation of gold. Then you take away the aluminum oxide. You have this gold pattern here. You have this gold nanodot ray. Then you can use the gold as the etching mask to etch into the gallium nitride to get this nanopillars. Or you can do this VLS process. This is the vapor liquid solid method for the nanowire growth. VLS, vapor liquid solid. We use gold as the catalyst to grow material like a silicon. So I will show you what is the VLS. Here is the vapor liquid solid method. So here you as the name indicates, you have the vapor and the liquid, and solid. So this is the LCl tetrachloride silicon plus hydrogen from silicon. So this one is the normal chemical vapor deposition process. So we have this chemical vapor deposition process. But this is the low pressure CVD. But for this chemical vapor deposition process, it will happen only at very high temperature, like 800 degrees. 800 degrees, there will be this chemical reaction. But in this case, so we have the gold. So gold is the catalyst. Then at the lower temperature, like 200 or 300 degrees, or maybe 400 degrees, there will be this chemical reaction will occur. When you have this chemical reaction, so the silicon will come into this liquid drop. Then we have too much silicon. The silicon become super saturated. So then silicon becomes super saturated. Then the silicon will come down. To the pillars. To the pillars. Then this pillar here will grow up and down and grow up and up. And this liquid droplet also is always on the top of the pillar. This is the VLS method to grow nanowires, silicon nanowire, and also other type of the nanowires. So where comes this liquid? Why we have this liquid? So we know that silicon is melted at more than 1,400 degrees. So gold is melted at a little bit over 1,000 degrees. But we have this gold silicon alloy. So we have this alloy. We have gold silicon alloy. It is melted at a much lower temperature. I think it's about this gold silicon alloy can melt at only 363 degrees. That's why you have this a liquid droplet at the interface. Because this one is the gold silicon alloy. Then you can see here, silicon come to here, then super saturated, then it will come to this silicon, and it will keep growing. So this is the VLS growth. In this example, the people use the AO as the tablet to grow carbon nanotube. This one from the professor Jimmy Xu. So he used to be a professor at the University of Toronto, but later on he went to the US to be a professor. So first, for the grow the carbon nanotube, we need some catalyst. Here the catalyst can be iron. The catalyst for the carbon nanotube can be iron, cobalt. So those are the good catalyst material for the growth of the carbon nanotube. So here the author use the cobalt. So how to deposit the cobalt on the bottom of the hole without deposition on top of the hole? So what you do, so this is not obvious, but what you do, when you do the deposition, there will also be the cobalt here, right? So when you do the deposition, there will be cobalt on the bottom, but there also will be the cobalt on the top. We also have cobalt on top. So how to remove the cobalt on top without removing the cobalt on the bottom? So what you can do, you do a argon ion. You do argon ion milling. You do argon ion milling. So when you do the argon ion milling, the wafer is tilted. You tilt the wafer. As a result, the argon go slanted, tilted instead. So the top part will be removed, but the bottom part is shadowed. The bottom part, the cobalt at the bottom, will not be removed by this tilted argon ion milling process. They can use the cobalt to grow the carbon nanotube. So the same group, they also grow a Y-shaped. They also grow the Y-shaped carbon nanotube. How to grow the Y-shaped carbon nanotube? So we need a Y-shaped. To grow Y-shaped carbon nanotube, so we need a Y-shaped AO. So how to form this kind of AO? How to form the Y-shaped AO? So as we said that, so here we use the low voltage. Here we use the high voltage. And the period equals 2.5 times the voltage, right? We know about this. So we have a higher voltage, you get larger pole and a larger pitch. We have smaller voltage, you get denser pattern, you get smaller pole. This we get this, they can grow a Y-shaped carbon nanotube. So the last example is the supercapacitor for the energy storage. So we know that for the capacitance, the formula is given by this is the formula. You can see, so the larger the surface area, the higher the surface area, the higher the capacitance. So how to have higher surface area? So this group they have a very smart idea. So they grow the capacitance using the internal wall area as the total area. They have the AO. They grow the 3 layers of the metal insulator metal. You have this metal dielectric. So you have this capacitor. So here the metal is titanium nitride, and this dielectric material is aluminum oxide. The other metal is also titanium nitride. But how to fill in the metal inside the pores? Inside the part very, very conformal filling. This is done by the ALD. I believe you have learned about ALD in the NE353. This is the atomic layer deposition. So we have this atomic layer deposition. You deposit layer by layer in an extremely conformal, very, very conformal. Layer by layer, a very, very conformal deposition. You can grow something like this, just follow the wall perfectly. If you do sputtering, this will not work. If you do the sputter, for example, you do the sputter. There will be some metal here, a little bit of metal here, more metal, So this is not conforming. When you do the sputter, lot of deposition on the top, not much deposition inside the pore. But when you do the ALD, you get this extremely conformal deposition. So you have very high capacitance. Then you have this connecting out to the top layer, titanium nitride. One layer, this is another titanium nitride. Then you have this green color here is the aluminum oxide. This way you get very, very high capacitance. This is the backside of aluminum oxide barrier. This is the barrier of the aluminum oxide. This is similar to the water cube. So now let's look at a nanosphere lithography. So nanosphere lithography. So we have the nanosphere. They will be self-assembled. This is self-assembling of the colloidal particles. You can see you have very nice long-range pretty periodic structures here. This is the monolayer self-assembly. This one is the three-dimensional self-assembly. Now we can use this kind of self-assembly pattern as the lithography method. So typically, the particle size is a few hundred nanometers. So the larger the particle, the easier to self-assemble into the more regular patterns. So the particle here, there are two popular choices for the nanoparticles. The first one is the polystyrene. Polystyrene is a popular choice of the nanosphere colloid. Another one is the silicon. But you can also buy easily silica nanospheres. There are quite a few ways to do the self-assembly process. The first one is called sedimentation. So you have a beaker, you have a beaker container, you have the liquid with the nanoparticles. Then the nanoparticle they will condense onto the bottom of the beaker. This way you get 3D self-assembled pattern. You get something like this. It will come to the bottom of the beaker. The second one is the evaporation of the solvent. So when you have the solvent get vaporized, the water will flow this way, and because of capillary force, you form this 1D or 3D self-assembled pattern. This one is called adsorption. You pattern some chemical pattern on the surface to absorb, to take the nanospheres. You can also apply some electrical field or magnetic field to get the self-assembly. This one is called biospecific self-assembly. You use some biomolecule to bring two particles together. This biomolecule can be DNA and complementary DNA or antibody antigen, or this kind of pairs. You can also make the surface some pattern to get the self-assembly. This one is important for the fabrication of the quantum dot devices. So those nanoparticles here can be quantum dot. This is the template on the droplet. So now let's look at how this thing works, evaporation of the solvent. So we have this, when you do the spin coating or cast coating, you have this, the water here will be vaporized. And when the water here will be vaporized, the water from the bulk, there will be convection flow. The water will flow this way. And the sphere will also come to the interface. So what's force bringing the sphere together? So what's force bringing the sphere? Why they touch each other? And this is because of the capillary force. So imagine you have two particles here. You have one particle here, another particle here, and you have this water. So you said you have the water, you have the liquid. Then you have the capillary force. So this capillary force will be like this, right? The capillary force will be something like this. So this capillary force will pull the two particles together. That's why you can see at the end they touch each other. So because of the surface tension, capillary force. So once they come together, they will be held together by the van der Waals force, hydrogen bond, and ionic interaction force. Then they will stay together. So in this example, so this is also the solvent evaporation. So this one is also solvent evaporation. So what do? You put your wafer here, and you have nanosphere inside the solution. So you draw slowly, you pull out slowly, there will be water evaporation there and self-assembly of the nanoparticles onto the substrate. So the speed of the withdrawal has to be very, very slow. It's only 60 micrometer per minute. You get this 3D self-assembly. So obviously, the easiest way to do the self-assembly is to use the semi-coating or drop coating. So you put a drop over the nanosphere solution, you do the semi-coating. By chance, you can form this monolayer. But this one is not so easy to control. So here you have the monolayer here, but you can see some places there are some void. There are a lot of void, right? No spheres on some places. And some places there can be a bilayer, there can be a double layer. This is not so well controlled. So a better way to do this one is to use the LB. If you just want one monolayer, you will use this one. So what is the LB? So what is the LB method? So this is the long-mirror broadcast method. So this is the Langmuir Blodgett method. So Langmuir, so he won the Nobel Prize. So he won the Nobel Prize, but she doesn't won the Nobel Prize. So you can see here, you can find a monolayer. Here you have this monolayer of the stearic acid, very thin monolayer of stearic acid. You can find this one. But here, what we have here is the nanosevere. So you can consider this molecule. You can consider this is like another sphere. So we have another sphere. It will form one monolayer of the nanosphere on the liquid surface. But it's the problem. You can see the sphere. They do not touch each other. They are separated by the voltage. So we need to bring the sphere. We need to push the sphere from one side to the other side, so that they can come together. They can come together and touch each other. So how to do this? So what do you do? So first you spread another sphere on the liquid surface. Then you put a drop of the oil. You put a drop of the molecule. This oil will spread. The oil will spread and push the sphere to the other side of the beaker. Then they will come together because they are pushed by this oil. The oil spread to push them together. Then you can put your wafer below. And you pick up monolayer of the nanosphere. This one give you better. This one give you better self-assembly of the monolayer, because normally we need monolayer for the pattern transfer. We do not need double layer. So this Langmuir-Blodgett method give you better self-assembly. So this process depends a lot. on the substrate surface. For example, in this substrate here, the wafer is cleaned by the perina and RCA. The perina is the mixture of the concentrated sulfuric acid and hydrogen peroxide. We know that this one is a very strong oxidizing agent. This is also oxidizing agent. So when they come together, it's very, very strong. And we mix them, it will become very hot. So then the polymer, the contaminant on the wafer will be burned away. So follow the perina, you can also do the RCA cleaner. So this one is also very, very strong. High temperature, very, very, very strong. It can make the surface really clean, remove all the contaminant. We get nice self-assembly. This is the chromic sulfuric acid, but this one, the surface is not so clean. You see the self-assembly is not very good. So what do we do with the non-severe lithography? What fabrication we can do? So this is the most typical process. You have you clean the wafer, you drop coat or the spin coat a monolayer of the nanosphere. Then you do the silver evaporation, and then you dissolve the sphere. The sphere is typically a polystyrene. So polystyrene can be dissolved by some solvent. You leave behind the silver. This is the silver pattern. The silver, you can see, the silver is at the gap of this nanospheres. So we have this kind of shape. So this is the white color is nanosphere. The red color here is the silver. So this work, the nanosevere lithography was first discovered in 1984. But it became widely utilized by the group Van Duyen group from Northwestern University, from this group. But he is not the professor. The professor is Van Duyen from Northwestern University. So this professor, he is a chemist. For the chemist, it's hard to do the clean room research. He does not want to use the clean room lithography. So he used this very easy way to make some noble metal nanostructures. So this is Professor Van Duyen, he discovered stress in 1976. So this professor, he discovered stress in 1976. Then he used this method. He used this non-severe lithography method to work for the stress substrate. The stress means surface enhanced Raman scattering. So surface enhanced Raman scattering. So it is a Raman scattering process. For the Raman scattering, it's proportional to the field power 4. So this field, this is the light. The light is electromagnetic field. So the Raman scattering is proportional to the electrical field of the electromagnetic field power 4. So we have very strong light. You get much higher Raman scattering. That's why it's called a surface enhanced Raman scattering. So how to get a very, very high electrical field? So you can imagine if you have something like this. So this is very sharp, right? It is very sharp. So when it is very, very sharp, here the electrical field will be very, very high. It will be very, very high. Then you get this stress effect, Raman scattering enhancement. This is one triangular shape. This is made of silver or maybe gold. So we have this one here. This is called a bow tie. Here have two triangular shapes. So the field here, the light intensity or electromagnetic field, the light intensity at the gap is even higher. This will get even higher enhancement. So this bow tie, the two triangular face each other, you can see here. So this is what you can see. We have the two triangular shape face each other. So this area here has very, very high light intensity. So you have very, very high stress effect. You can also use double layers. So we have double layers. You get this hexagonal array of the hexagonal array of this nano patterns. This double layer. The gap is defined by this layer here, double layer. You can also do the angle evaporation. You tilt the wafer to one deposition. Then you tilt the wafer again to do a second deposition. Then you put the wafer flat. You have this deposition. You get this. Get this three layers. Right? You get this kind of patterns. You can also shrink the sphere. You use oxygen polymer to shrink the sphere. Then the sphere becomes smaller. Then you deposit the metal. You evaporate metal and remove nanosphere. You get this whole array. So here you get this pattern here. You get this bow tie array. So here you get this whole array. But actually, when the sphere is shrunk, it's not like this. So you can imagine if we have this polystyrene sphere. So after etching, it becomes maybe something like this. Right? If we have oxygen polymer here. We have oxygen polymer here, etch it becomes something like this, rather than like this. But it doesn't matter. So in the end, you get this whole pattern. But this is another application of the nanosphere. So what do you do? So first, you grow the nanosphere. You have this self-assembled nanosphere. Then you pour PDMS. You pour PDMS onto the nanosphere. Then you cure it. You cure the PDMS. So in that, you get this nanosphere. You get the nanosphere embedded in the PDMS. This is PDMS. You have nanosphere inside the PDMS. So we know that PDMS can be swelled, can be swollen by many solvents. When they are swollen, it becomes the distance between the nanosphere will become bigger. When you have bigger distance, the color will be different. The color will be different. That's why it said you can print color patterns without using the pigment. When you have different period, you have different color. This is like a grating effect. Yeah, this is like a grating filter. So the color, as we have seen before, so something like this. You have the one pattern here. We have seen the grating pattern here. The light comes in and come to your eye. Your eye is here. So you can see the color here. The color given by something like this. Right? The color given by something like this. You can see the larger the pitch, the longer the wavelength. So that means the color will become longer wavelength, as you can see here. This one is the before swelling green color. After swelling, it got a longer wavelength. It become red color. But this one can be used as a paper. This is used as the paper. So what do you use? So the ink is the solvent. You have solvent. And the ink. So when you write on the paper, the solvent will swell the paper, so it become red color here. So in the other area, it's still green. But this one will not last very long. You can see after swelling, it comes down to 2 minutes. After 2 minutes, the letter will be gone after 2 minutes. This is like a kind of paper. You do not need a reader. You don't need a reader to read it. You can write for many times. the letter will disappear automatically. I know some people use this kind of thing to do the signature. You sign a paper, then the people take your signature. Then after some time, they found out the signature is gone. So we have talked about non-severe lithography. So here, this one is not non-severe lithography. This is not non-severe lithography. But because I do not have many slides, so I just put it at the end. This is the DNA templated subassembly. In this case, you can see the DNA. We know DNA is negatively charged. So this way, you can have some metal ions. Those positive metal ions can be bonded to the DNA molecule, so you form some metal nanowires. In this case, it is the palladium. Palladium can be reduced to the DNA to form this palladium nanowire. In this example here, this from the Chad Merkin group. This is the same group who discovered a different The different lithography is also discovered by the same group, Chad Merkin group. So in this work, so you put some DNA molecule onto the nanosphere. DNA molecule onto the nanosphere. This is DNA. This one is the complementary DNA. Then they will come together. You form some nanosphere subassembly using the DNA as the template. The last example is called a DNA subassembly to form this kind of patterns. You can form this called the holiday junction. You form this kind of pattern, this kind of 2D pattern using the DNA. Now this one is called, there is a name for it. It's called a DNA origami. Oh, what's wrong? It's called DNA origami. I will show what is DNA origami. So DNA origami is the non-scale folding of the DNA to create arbitrary 2- and 3-dimensional shapes. So what do? You design the sequence, you design the base sequence of the DNA, then it will be folded. So when they are folded, you can form really arbitrary 2D or 3D pattern. It can be very, very complicated. And right now there is the software that you can use to design very, very complicated patterns. So those are the examples of the DNA origami subassembly. You can see here, for example, this one. So those molecules, this complicated patterns. This one is like I think of them, they are like just one DNA molecule. So one DNA chain, you design the sequence such that it will be folded like this or folded like the face. You can also do this kind of, you see, 3D patterns, like a box, like a cage, 3D patterns. And some people even make something, you can even make a box. This box is made of the one long DNA chains. It will be self-folded. It will be folded into this complicated shapes. Thanks very much.